The universe is not just expanding, it is flying apart faster every second. This discovery of cosmic acceleration shattered a century of scientific belief, revealing that an unknown force governs our reality. By the end of this journey, you will understand why this mystery suggests a form of energy we barely understand, one that holds the keys to the ultimate fate of all existence. We will uncover how astronomers stumbled upon this shocking truth and why it points to a cosmos dominated by something called dark energy, an invisible presence making up most of everything. How do you think a discovery that rewrites all the rules should make us feel? Mount Wilson in the 1920s was a quiet, remote peak, home to the world's most powerful telescope. There, a meticulous astronomer named Edwin Hubble spent long, cold nights collecting light that had traveled for millions of years. He was not looking for a mystery, he was simply measuring, cataloging the faint smudges of light we now know as other galaxies. What he found in their light was a subtle but undeniable shift, a stretching toward the red end of the spectrum. This redshift was the universe's fingerprint, a telltale sign that those distant islands of stars were all racing away from us. The farther away a galaxy was, the faster it appeared to be receding. This single, elegant observation shattered the ancient belief in a static, unchanging cosmos. The universe was not standing still. It was growing, stretching, expanding in every direction like the surface of an inflating balloon. This revelation was monumental. It gave us a dynamic, evolving universe with a history, a beginning we would later call the Big Bang. For decades afterward, this became the central story of cosmology. Scientists reasoned that if everything was flying apart, the mutual gravitational pull of all the matter in the cosmos must be acting like a cosmic brake, tirelessly working to slow that expansion down. The great question became not if the universe would slow, but how. Would the pull of gravity be strong enough to one day halt the expansion and reverse it, leading to a dramatic big crunch? Or would it merely slow the expansion to a gentle, eternal coasting? Both possibilities were captivating, but they shared one core assumption, a prediction so logical it seemed unassailable. The expansion of the universe had to be decelerating. This expectation was woven into every textbook, every model, the very fabric of how we understood cosmic destiny. The stage was set not for a quiet confirmation, but for a discovery so shocking it would feel like the universe itself had broken its own rules. That logical prediction of a slowing cosmos held for 70 years. Then, in the late 1990s, two groups of astronomers set out to measure the universe's deceleration with a new kind of cosmic ruler. They turned to the violent deaths of ancient stars, events known as Type 1, a supernova. These stellar explosions are remarkably consistent, always reaching the same peak brightness. This makes them perfect standard candles. If you know how bright something truly is, you can measure how bright it appears from Earth and calculate its precise distance, just like judging how far away a street lamp is by how dim it looks. By finding these supernovae in incredibly distant galaxies, the teams, one led by Saul Perlmutter and another by Schmidt and Adam Riess, were looking billions of years back in time. They aimed to see how much the expansion had slowed over cosmic history. The process was painstaking, requiring flawless observations from the world's largest telescopes and complex analysis. When the final data came in, it pointed to something impossible. The most distant supernova, the ones from the deepest past, were fainter than they should have been. This meant they were farther away than any model of a decelerating universe could allow. There was only one soul-shaking conclusion. The expansion of the universe was not slowing down at all. It was speeding up. Gravity, the force that shapes galaxies and holds planets in orbit, was losing a cosmic tug of war against something else. The researchers were stunned. They checked and rechecked their work, searching for errors in the dust of distant galaxies or flaws in their instruments. The result held. In 1998, they announced their findings to the world, a revelation so profound it felt like the ground of physics itself had shifted. This discovery of cosmic acceleration, which would later earn the Nobel Prize, did not solve a mystery. It created a far deeper one. If the universe's expansion is accelerating, what invisible hand is pushing it apart? The universe had broken the most fundamental rule we thought we knew. For every action, there is an equal and opposite reaction. But in the grand theater of the cosmos, gravity seemed to be acting alone. According to Einstein's theory of general relativity, gravity is not just a force between objects. It is the curvature of spacetime itself, shaped by the presence of mass and energy. Every star, every galaxy, every speck of dust creates a tiny well in the fabric of the universe, pulling everything else toward it. On the scale of the entire cosmos, this collective pull from all the matter that exists should act like a universal brake, relentlessly working against the momentum of the Big Bang, slowing the expansion down. Imagine rolling a ball up a very long, gentle hill made of soft sand. Even if you give it a mighty throw, the friction and the constant pull of the hill will eventually cause the ball to slow, stop, and then roll back down. For 70 years, we believed the universe was on that uphill climb, destined to eventually slow to a halt. The supernova data revealed something impossible. The ball is not slowing down, it is speeding up, as if the hill itself has turned into a downward slope pushing it forward. This means something is actively working against gravity, not just matching its pull, but overwhelming it. This something must possess a repulsive gravitational effect, a kind of anti-gravity woven into the empty spaces between galaxies. It is not a force in the traditional sense, but a property of space itself. As the universe expands, more space comes into existence, and with it, more of this repulsive energy, creating a runaway feedback loop that pushes galaxies apart faster and faster. This is not a minor tweak to our equations. It is a fundamental challenge, revealing that either our understanding of gravity is incomplete on the largest scales, or that the vacuum of empty space is not empty at all, but seething with a form of energy whose nature we have barely begun to comprehend. It points unequivocally toward physics beyond our current standard model, a hidden chapter in the book of reality we have yet to read. To give this invisible driver a name, scientists called it dark energy. It is a placeholder, a label for our profound ignorance, assigned to whatever is causing the acceleration of the cosmos. We must be clear about what this name means. Dark energy is not a substance you could ever touch or contain. It is not a cloud of exotic particles or a hidden fifth force swirling between the stars. Instead, the leading idea is that it is a fundamental property of the vacuum of space itself. Think of the emptiest void you can imagine, a region between galaxies utterly devoid of matter. According to this concept, that void is not truly empty. It possesses a baseline energy, a gentle, uniform tension inherent to the fabric of spacetime. This energy is everywhere, and as the universe expands and new space is created, this energy density does not dilute or thin out. More space means more dark energy, which creates more repulsive push, leading to ever faster expansion. It is a runaway process built into the architecture of reality. This idea has a fascinating historical echo. Decades before the accelerating universe was discovered, Albert Einstein introduced a mathematical term into his equations of general relativity called the cosmological constant. He added it reluctantly as a kind of fudge factor to force the equations to describe a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble later proved the universe was expanding, Einstein famously called the cosmological constant his greatest blunder and removed it. Now, in a stunning twist of fate, that discarded idea has returned as the leading candidate to explain dark energy. It represents the energy of empty space, a constant background hum that exerts negative pressure. This negative pressure is the key. While matter and radiation create positive pressure that pulls things together through gravity, the negative pressure of dark energy does the opposite. It generates a kind of repulsive gravity, acting as a constant push on the cosmos itself. Today, measurements tell us dark energy makes up about 70% of the entire energy budget of the universe. It is not just a component, it is the dominant influence, the conductor now steering the symphony of cosmic expansion. Yet for all its overwhelming presence, we know almost nothing about it. We see its dramatic effects, but its true origin and fundamental nature remain one of the deepest enigmas in all of science. We have given the mystery a name, but the entity itself continues to hide in plain sight, woven into the empty spaces between everything we see. The story of dark energy is intertwined with one of history's most famous scientific regrets. Albert Einstein, after formulating his magnificent theory of general relativity, faced a problem. His equations described a dynamic universe, one that should either be expanding or contracting. Yet every astronomer of his era was convinced the cosmos was eternal and unchanging, a static backdrop of fixed stars. To reconcile his brilliant theory with this incorrect belief, Einstein made a small but profound adjustment. He introduced an extra term into his equations, a fudge factor he called the cosmological constant. This term represented a kind of repulsive energy embedded in space itself, a counterbalance to gravity that would hold the universe in a perfect, fragile equilibrium, preventing it from collapsing under its own weight. When Edwin Hubble later demonstrated the universe was indeed expanding, Einstein saw his error with devastating clarity. He had missed a chance to predict one of the greatest discoveries in science. He famously discarded the cosmological constant, calling it his greatest blunder. For decades, the term was relegated to a footnote, a curious mistake by a genius. But the universe, it seems, has a deep sense of irony. That discarded idea, that mathematical fudge factor, has been resurrected from the ash heap of history. Today, the cosmological constant is the leading and simplest explanation for dark energy. It is no longer seen as an error, but as a potential revelation, a description of a constant energy density inherent to the vacuum of space itself. In this modern view, empty space is not nothing. It is a simmering sea of quantum activity, and the cosmological constant represents its baseline energy, a gentle, relentless pressure that causes the acceleration we observe. This elegant solution, however, creates a problem of unimaginable scale. When physicists use our best theory of the quantum world to calculate how much energy should be bubbling in the vacuum, the number they get is catastrophically, incomprehensibly wrong. The theoretical prediction exceeds the observed value of dark energy by a factor of 1 followed by 120 zeros. This is not a small rounding error. It is the worst mismatch between theory and observation in the entire history of science. To grasp the size of this failure, imagine predicting the weight of a single grain of sand, and your theory instead gives you the mass of the entire observable universe. This discrepancy, known as the cosmological constant problem, screams that we are missing something fundamental. Either our understanding of the quantum vacuum is deeply flawed, or the cosmological constant is not the final answer, and dark energy is something even stranger. It highlights a terrifying gap in our knowledge, showing that the dominant component of our reality operates by rules we have not yet written. Faced with a cosmological constant that feels both perfect and deeply problematic, scientists have been forced to consider other possibilities. What if dark energy is not a constant feature of space, but something that changes, something that evolves? This idea leads us to a concept called quintessence. Named after the ancient Aristotelian fifth element that filled the heavens, Quintessence proposes that dark energy is not a static property of the vacuum, but a dynamic field that permeates the cosmos. Think of it less like a fixed background hum and more like a cosmic weather system, with subtle variations in density and strength over both time and space. This field would act as a kind of fifth fundamental force, one with a repulsive gravitational effect. Unlike the stubborn cosmological constant, a quintessence field could potentially interact with other forms of matter and energy, however weakly. It could also evolve, meaning its influence on the expansion of the universe might have been different in the distant past and could change again in the far future. This dynamism offers a tantalizing escape from the fine-tuning problem of the cosmological constant. Instead of requiring a miraculously precise, unchanging value set at the dawn of time, a quintessence field could have naturally rolled into its current state, making our accelerating universe seem less like a bizarre accident and more like a natural outcome. Some theories even suggest this mysterious field could be linked to other profound puzzles, like the nature of the inflation that blew up the universe just after the Big Bang, or to undiscovered realms of particle physics. Quintessence paints a picture of a living, breathing cosmos where the engine of expansion itself is in motion, but there is another, more radical path entirely. What if we have been asking the wrong question? Instead of inventing a new form of energy to explain the acceleration, perhaps we should reconsider the force we thought we knew. This is the realm of modified gravity theories. These ideas propose that Einstein's theory of general relativity, while spectacularly successful everywhere we have tested it, might break down on the very largest scales of the universe. Perhaps gravity itself behaves differently across cosmic distances, weakening in a way that mimics the effect of a repulsive force. Imagine the rules of magnetism subtly changing for objects more than a mile apart. You would see puzzling attractions and repulsions that seem to demand a new kind of magnet, when in reality, it was just magnetism playing by a different rulebook. Modified gravity theories attempt to rewrite that cosmic rulebook, tweaking the equations of general relativity so that the observed acceleration emerges naturally from the gravity of ordinary matter, with no dark energy required. It is an elegant and compelling vision, a universe governed by a single, modified force. Yet this path is fraught with its own immense challenges. Any successful theory must not only explain the accelerating expansion, but also flawlessly account for every other confirmed prediction of general relativity, from the orbit of Mercury to the bending of light around galaxies. So far, every proposed modification has stumbled when faced with the full suite of precise astronomical data, often creating more problems than it solves. The choice between a mysterious new energy and a modified old force represents a fundamental fork in the road of physics, and at this moment, the evidence still points toward something filling the void. This staggering breakdown of reality is the ultimate lesson in cosmic humility. If we were to take a complete inventory of everything that makes up our universe and bake it into a cosmic pie, the slice belonging to the world we know and see would be almost laughably small. The atoms that form every star, every planet, every living creature, and every speck of interstellar dust, what scientists call baryonic or ordinary matter, accounts for less than 5% of the total cosmic budget. It is the rarest ingredient in the cosmos. The next piece of the pie, making up about 27%, is something we cannot see but can feel: the powerful gravitational grip of dark matter. This invisible scaffold holds galaxies together and shapes the large-scale structure of the universe. Yet even this mysterious substance is not the main event. The overwhelming majority of the pie, a dominant 68%, is the force we have been discussing: dark energy. Let that sink in for a moment. Everything we have ever observed through every telescope in history, every chemical element forged in stellar furnaces, every structure that light can reveal, is less than a 20th of what exists. The remaining 95% is dark, invisible, and profoundly unknown. This cosmic inventory is not a guess. It is a robust picture pieced together from multiple, independent lines of evidence that all point to the same shocking conclusion: the precise measurements of the cosmic microwave background radiation, the large-scale distribution of galaxies, the observed acceleration from distant supernova, and the way galaxies cluster and move. They all converge on these same numbers. This means dark energy is not a minor curiosity or a theoretical footnote. It is the primary constituent of reality itself. It is the stage upon which the drama of galaxies and stars plays out, the unseen ocean in which all visible matter floats. This composition dictates everything about the universe's large-scale evolution and its ultimate fate. We are living in a cosmos where the force we understand the least is the one calling all the shots, accelerating the expansion of space and steering the destiny of all existence. The story of the universe is in essence the story of dark energy, and we are only just beginning to read the first page. That single supernova discovery could have been a fluke, a cosmic misreading. But science builds truth through convergence, where multiple paths lead to the same startling destination. The acceleration of the universe is not just one measurement, it is a chorus of evidence singing the same unsettling tune. The first and most profound of these voices comes from the very beginning of everything, from the afterglow of the Big Bang itself. We call it the cosmic microwave background, a faint, cold light that fills every cubic inch of the sky. This radiation is a snapshot of the infant universe, taken when it was just 380,000 years old, a fossilized imprint of its earliest moments. By studying the minute patterns in this light, the tiny hot and cold spots, cosmologists can deduce the geometry of the cosmos and its total energy budget. The results are exquisitely precise. The universe appears geometrically flat, which tells us its total density of matter and energy must be exactly at a critical value. But when we add up all the ordinary matter and dark matter we can detect, we come up drastically short. Something must be making up the difference, a smooth, uniform energy that does not clump like matter. That something, of course, is dark energy. The patterns in that ancient light require its presence and even tell us its abundance, a figure that matches the supernova measurements with uncanny accuracy. It is as if we asked the newborn universe a question, and its whispered answer, frozen in time for over 13 billion years, confirmed our most shocking modern discovery. This cosmic fingerprint is not the only independent check. Look at the universe's large-scale structure, the vast cosmic web of galaxies and clusters stretching across billions of light years. This web did not form randomly. It grew from tiny seeds in the early universe, amplified by gravity over eons. Dark energy, with its repulsive push, acts as a cosmic brake on this growth. As it came to dominate the universe's energy budget, it began to suppress the formation of new giant structures. Astronomers can map this web through immense surveys, charting the positions of millions of galaxies and measuring how they have clustered together over cosmic time. What they see is a clear signature of that suppression, a telltale sign that something began counteracting gravity's pull on the largest scales, slowing the growth of the cosmic web. The timing and strength of this effect align perfectly with an accelerating expansion driven by dark energy. It is a different kind of observation, using the architecture of the universe itself as the evidence, and it points to the same conclusion. When you have a mystery this profound, you need more than one clue. Here, we have the dying stars telling us the expansion is speeding up. The ancient light telling us the universe's geometry demands a mysterious energy, and the frozen growth of the cosmic web telling us a repulsive force has taken hold. These are not echoes of the same observation. They are separate melodies that harmonize into a single, undeniable truth. The phenomenon is real. The acceleration is happening. And the universe we live in is fundamentally stranger and more wonderfully puzzling than we ever dreamed. The ultimate fate of all existence hinges on the true nature of this invisible driver. If dark energy is indeed a simple cosmological constant, a steady and unchanging presence, then the future of our universe is one of profound and silent isolation. This is the scenario scientists call the Big Freeze or heat death. As the acceleration continues unabated, the space between galaxy clusters will stretch at an ever-increasing rate. Distant galaxies we see today will one by one cross a cosmic horizon, their light stretched beyond detectability and vanish from our sky. Our own Milky Way, merged with Andromeda and a few satellite galaxies, will become an island universe in a sea of nothingness. Over trillions upon trillions of years, stars will burn through their fuel and wink out. Black holes will slowly evaporate through a process known as Hawking radiation. The universe will become an unimaginably vast, ever-expanding void, filled only with a faint, cold sea of radiation and isolated subatomic particles so far apart they will never interact again. It is a destiny of ultimate stillness, where the cosmos achieves a state of maximum entropy, a uniform, lukewarm bath with no energy gradients left to drive any process, any structure, or any form of life. This is the most likely forecast based on our current best data, a slow fade to black on a timescale that dwarfs all of human history. But there exists a far more dramatic and far more violent alternative. What if dark energy is not constant? What if it is a form of quintessence that grows stronger over time? This possibility leads to a hypothesis known as the Big Rip. In this scenario, the repulsive push of dark energy does not just accelerate the expansion of space between galaxies, it intensifies. Its strength would eventually overcome every force that holds structures together. First, the gravitational bonds tethering galaxy clusters would be severed. Then, individual galaxies themselves would be pulled apart, their stars scattered into the deepening void. As the force grows, it would next tear apart solar systems, separating planets from their suns. Closer to the end, the gravitational hold of a planet on its own atmosphere would fail. In the final moments, the very fabric of matter would unravel. The forces that bind atoms together, and even the nuclear forces holding atomic nuclei intact, would be overwhelmed. In a finite, calculable future, every star, every planet, every molecule, and every fundamental particle would be ripped apart from its neighbors, torn into disconnected fragments by the runaway expansion of space itself. The universe would end not with a whimper, but with a catastrophic shredding of reality's basic structure. These two visions, the silent freeze and the violent rip, illustrate a staggering truth. The most fundamental question about our cosmos, its final destiny, remains entirely unanswered because we do not understand the dominant component of reality. The choice between an eternal, cold emptiness and a finite, explosive end rests on properties of dark energy we have not yet measured. Is its strength truly constant, or is it dynamic? Does it interact with itself or with other fields? The answers are not philosophical musings, they are physical parameters waiting to be discovered. This means the fate of everything, from the largest galaxy cluster to the smallest grain of sand, is currently encoded in a mystery that makes up nearly 70% of the universe. Our story, and the story of all existence, is being written by a hand we have only just begun to feel. Studying dark energy is like trying to measure the shadow of a ghost using only a ruler made of starlight. It emits nothing, absorbs nothing, and reflects nothing. We cannot see it, touch it, or isolate it in a lab. The only way we know it exists at all is by observing its single, monumental effect, the relentless acceleration of the cosmos itself. This makes it one of the most fiendishly difficult problems in all of science. How do you measure the properties of something that is, by its very nature, invisible? The answer lies not in looking at the thing itself, but in meticulously mapping its influence on everything else over the vast expanse of cosmic time. We must become cosmic historians, reconstructing the entire life story of the universe's expansion to see how the push of dark energy has changed. To do this, astronomers are building the most ambitious sky surveys in history, instruments of staggering scale and precision designed to take a forensic census of the heavens. Projects like the Dark Energy Survey have already spent years imaging hundreds of millions of galaxies, charting their shapes and distances, but this is just the beginning. We are on the cusp of a new era driven by observatories like the Vera C, Rubin Observatory, with its gigantic mirror and camera the size of a small car, which will scan the entire southern sky every few nights for a decade, cataloging billions of galaxies and discovering millions of supernova. Meanwhile, the Euclid space mission, a telescope orbiting far from Earth, is creating an exquisitely detailed three-dimensional map of the universe, measuring the subtle distortions in the shapes of galaxies caused by dark matter, which itself is sculpted by the repulsive push of dark energy. These are not just bigger telescopes, they are entirely new kinds of eyes on the cosmos. Their goal is phenomenally precise, to measure the expansion history of the universe not at a few points in time, but continuously across billions of years. They will track how fast galaxy clusters formed and how the cosmic web grew, looking for the specific imprint left by a dynamic dark energy. The critical question they aim to answer is this: has the strength of dark energy's repulsive push remained constant, or has it changed? If it is perfectly constant, it points firmly to Einstein's cosmological constant, a fixed feature of space. But if we detect even a tiny variation in its strength over cosmic history, it would be a revolution. It would mean dark energy is something like quintessence, a dynamic field that evolves, opening doors to entirely new physics. This measurement is a task of almost unimaginable subtlety, trying to discern a minute drift in the acceleration rate over eons, a signal buried in petabytes of data and hidden behind countless other astrophysical effects. It is a testament to human curiosity that we are attempting to solve a mystery woven into the fabric of empty space by surveying the light from billions of ancient suns. The answer, when it comes, will not arrive with a bang, but as a statistical whisper from the data, a whisper that will tell us whether the universe is destined for a quiet freeze or a more dramatic end. This staggering mismatch between prediction and observation is not a minor puzzle. It is a screaming alarm bell in the heart of physics. It reveals a profound disconnect, a theoretical desert where our two most successful descriptions of reality simply stop talking to each other. On one side, we have quantum field theory, the magnificent framework that explains the behavior of the very small, the dance of subatomic particles and forces. It tells us that what we call empty space, the vacuum, is not empty at all. According to quantum principles, it is a seething, bubbling foam of virtual particles constantly flickering in and out of existence. This quantum frenzy should endow every tiny volume of space with an enormous intrinsic energy, a staggering density of vacuum energy. On the other side, we have general relativity, our majestic theory of gravity, and the very large, which describes the curvature of spacetime by mass and energy. When cosmologists plug the observed value of dark energy into Einstein's equations, they get a number so infinitesimally small it feels like a rounding error next to zero. The vacuum energy predicted by quantum mechanics is larger than the observed dark energy by a factor of 1 followed by 120 zeros. To put that incomprehensible scale into a human analogy, it is the difference between predicting that a single drop of water weighs as much as all the oceans on Earth. This is not a case of being off by a little. It is a catastrophic failure of our theories to describe a fundamental feature of the cosmos. This mismatch has a name, the cosmological constant problem, and it is arguably the single worst theoretical prediction in the history of science. It tells us in no uncertain terms that our understanding of the universe at the quantum scale and our understanding of the universe at the cosmic scale are fundamentally incompatible in their current forms. They are two different languages describing the same reality, and they give us completely different translations for the energy of nothingness. Dark energy, therefore, is more than just a mysterious component of the universe. It is the key clue, the glaring symptom of a deeper illness in the foundations of physics. It is the observable proof that we are missing a crucial piece, a theory that can seamlessly bridge the world of the quantum and the realm of space-time curvature. This is the holy grail of modern physics, a theory of quantum gravity. For decades, this quest has lived in the domain of abstract mathematics, with proposals like string theory, which suggests the fundamental ingredients of reality are tiny, vibrating strings, or loop quantum gravity, which proposes space-time itself is woven from a network of discrete loops. These are profoundly complex ideas, often untestable with today's technology, but dark energy changes that. It provides a concrete, measurable target for any candidate theory of quantum gravity. A successful theory must not only explain how gravity emerges from the quantum world, it must also naturally produce or allow for the existence of a vacuum energy that is not enormous, but almost exactly zero, or rather, precisely the tiny, constant value we observe driving cosmic acceleration. It must explain why the frenetic quantum buzz cancels itself out to such an exquisite degree, leaving behind only this faint, smooth residue that we call dark energy. In this light, the acceleration of the cosmos is not an isolated mystery. It is a cosmic signpost pointing directly toward the next great revolution in our understanding. The universe is showing us where our current maps end and the uncharted territory of a unified reality begins. The void is not empty, it is asking us a question we do not yet know how to answer. This uncomfortable gap between prediction and reality forces us to ask a deeply unsettling question. What if the value of dark energy is not something physics can predict from first principles? What if it is simply an accident of our cosmic address? This line of thinking leads to one of the most debated ideas in modern cosmology, the Anthropic principle, and its dramatic setting, the multiverse. The argument begins with a simple observation. The value of the cosmological constant we measure is bizarrely fine-tuned for life. If it were even slightly larger, the repulsive push would have been so strong in the early universe that it would have ripped apart the delicate density fluctuations before they could collapse into galaxies and stars. No galaxies means no planets and certainly no observers. If it were slightly smaller or negative, gravity would have dominated sooner, recollapsing the universe into a big crunch long before complex life could ever arise. We exist, therefore, in a very narrow window where dark energy is small enough to allow structure, but not zero. From a traditional physics perspective, this looks like a miraculous coincidence begging for an explanation. But from the multiverse perspective, it is not a coincidence at all. It is a selection effect. Imagine an infinite cosmic landscape, a vast and perhaps eternal multiverse, where every possible version of physical law plays out in separate, disconnected regions or bubbles. In most of these bubbles, the cosmological constant is enormous, leading to a rapid, empty expansion or a swift collapse. Universes form and vanish in an instant, sterile and unobserved. But in a vanishingly rare subset of these bubbles, through sheer random chance, the constants align in the narrow, life-permitting range. We, of course, can only find ourselves in one of those rare, hospitable bubbles. Our universe is not special because the laws were designed for us. We are here because we could not possibly arise anywhere else. This is the anthropic principle in its most provocative form, shifting the explanation for dark energy from a fundamental law of physics to a kind of cosmic environmental selection. It moves the question from why are the laws this way to why do we observe these laws. For some theorists, this is a powerful, even necessary, framework that dissolves the fine-tuning problem by embedding our universe in a much larger, more varied reality. For others, it represents a profound philosophical retreat, a surrender of science's traditional goal to find unique, predictive explanations from underlying principles. If any value is possible somewhere in the multiverse, then explaining our specific value becomes a matter of statistics and our own existence, not a deduction from a beautiful, unified theory. This debate touches the very heart of the scientific endeavor, challenging what we consider a satisfactory explanation. Is it enough to say we live in a universe compatible with our existence because all the others are silent? Or must we push further, demanding a theory that uniquely predicts the gentle whisper of dark energy we measure? The multiverse idea, while speculative and currently untestable in the traditional sense, forces this confrontation. It suggests that the deepest answer to the mystery of cosmic acceleration may not lie in a new equation, but in a radical reimagining of reality's vastness, where our entire cosmos is but one page in an infinite library of possibilities, most of which are blank. The universe's deepest mysteries are now being explored not just with telescopes, but within the silent, humming halls of supercomputers. These machines allow us to perform an extraordinary kind of experiment, one where we build entire virtual universes from scratch, set them in motion, and watch them evolve over billions of simulated years. This is the realm of cosmological simulations, and they have become an indispensable tool in our quest to understand dark energy. Since we cannot manipulate the real cosmos in a lab, we create a digital one, a vast, intricate model where we control the ingredients and the rules. We start with the initial conditions just after the Big Bang, a nearly uniform soup of matter and energy seeded with tiny quantum fluctuations. Then we let the simulation run, programming in the known laws of physics, gravity, the behavior of dark matter, the hydrodynamics of ordinary gas, and crucially, a parameter representing dark energy. The supercomputer calculates the gravitational attraction between trillions of particles of dark matter, watching as they clump together to form the cosmic web, the filamentary backbone of the universe. Within that web, ordinary matter follows, cooling and collapsing to form virtual galaxies and stars. All the while, the background expansion of space is driven by the dark energy parameter we have chosen. We can run this simulation forward over 13.8 billion years in a matter of weeks or months, generating a complete, dynamic history of a cosmos that has never existed outside of a server farm. The result is a breathtaking synthetic universe, a digital twin we can explore from any angle at any moment in its history, but the true power lies in comparison. Scientists then take this simulated cosmos and hold it up against our real, observed universe. They compare the large-scale structures, the distribution of galaxy clusters, the shapes and sizes of galaxies, and the overall expansion history. Does the virtual universe, with our assumed model of dark energy, produce a cosmic web that looks like the one we see in sky surveys? Do its galaxies form at the right times and in the right numbers? Does its expansion accelerate in precisely the way our supernova data indicates? If the simulation matches reality, it lends powerful support to the dark energy model we used. If it does not match, it tells us our assumptions are wrong. We can then adjust the parameters, run the simulation again, and see what happens. What if dark energy is not constant but grows stronger? We input that behavior and watch the virtual cosmos tear itself apart in a premature Big Rip, or perhaps expand too quickly to form any galaxies at all. By seeing which simulated universes end up looking like our own, we can effectively rule out entire families of theories. These digital laboratories allow us to test scenarios that are impossible to observe directly, like the universe's fate trillions of years from now, or to rewind time and see how different forms of dark energy would have altered the universe's infancy. It is a process of cosmic trial and error, using the sheer calculating power of silicon to explore the infinite possibilities hidden within our equations, narrowing down the properties of the one component we cannot see by meticulously checking which version of it builds a world that looks like home. One of the biggest points of confusion in modern cosmology is the simple similarity of two names. Dark energy and dark matter sound like they could be two sides of the same strange coin, but in reality, they are cosmic opposites with entirely different roles in the story of the universe. They share only two things in common. We cannot see them with any telescope, and the word dark simply means they do not emit, absorb, or reflect light. Beyond that, their natures and their effects could not be more different. Think of dark matter as the invisible skeleton of the cosmos. It is a form of matter, which means it has mass and is subject to gravity's attractive pull. It clumps together, forming vast halos around galaxies and weaving the immense cosmic web that spans the universe. We know it is there because we can see its gravitational handiwork, the way it bends light around galaxies and dictates how stars orbit within them. Without dark matter's extra gravitational glue, galaxies would fly apart. It is a cosmic architect, a builder of structure. Dark energy, on the other hand, is the great dismantler. It is not matter at all, and it does not clump or gather. It appears to be perfectly smooth, a uniform presence filling every cubic inch of space with the same gentle tension. Its effect is repulsive, not attractive. While dark matter pulls things together through gravity, dark energy pushes them apart by stretching the very fabric of space between them. One builds the cosmic cities, the other is making the roads between those cities grow longer at an ever-increasing rate. They are two distinct actors in the cosmic play, one holding the stage together, the other relentlessly expanding the theater itself. Another common misconception is to think of dark energy as a kind of radiation or a force, like light or magnetism. It is not carried by particles like photons that we could potentially detect. The leading idea is far stranger. It is better understood as a property of empty space itself, a latent energy inherent to the vacuum. This is why it is so difficult to study. We are not looking for a hidden particle. We are trying to measure a characteristic of nothingness. This distinction is crucial for understanding why the discovery of cosmic acceleration was such a monumental, paradigm-shattering surprise. Scientists were not expecting to find a new form of matter. They were prepared for that possibility. What they found was evidence that empty space itself possesses a dynamic, dominant energy that defies our everyday intuition. It revealed a universe where the void is not passive, but active, where nothing is really something, and that something is calling the tune for the fate of all we see. Clearing up these misunderstandings is the first step toward grasping the true, profound weirdness of our cosmos, a place where the most familiar forces are overshadowed by mysteries written in the dark. This profound imbalance in the cosmic ledger forces a humbling perspective shift. For all of human history, we have believed the universe was made of the things we could see and touch, the stuff of stars and stones and living things. Our science, our philosophy, and our stories have all been built upon this tangible reality. Yet the data now tells us this familiar world is a mere afterthought, a delicate shimmer of light on the surface of a deep, dark, and incomprehensible ocean. 95% of the cosmos operates by rules we have not yet deciphered, in forms we cannot directly perceive. This is not a small gap in our knowledge. It is a yawning chasm at the very foundation of existence. It challenges a deeply held intuition, the belief that the universe is, at its heart, knowable through the careful application of human reason and observation. We have mastered the atom, unraveled the code of life, and sent probes beyond our solar system. Yet we must now confront the possibility that the true nature of reality might be permanently veiled, its dominant components forever just beyond the reach of our finest instruments. What does it mean for our search for understanding if the stage itself is made of a material we cannot define? This question moves us from the realm of pure astrophysics into the domain of philosophy. It touches on the very limits of scientific inquiry. Science thrives on observation, measurement, and repeatable experiment. But how do you experiment on something that is, by definition, the absence of signal? How do you build a model of a force that seems woven into the empty spaces between your measuring devices? The elusiveness of dark energy and dark matter suggests that some truths about the universe may be inferred only indirectly, through their shadows and their effects on the tiny sliver of reality we can see. We may be like deep-sea creatures who have only just begun to suspect the existence of water, sensing its pressure and its currents but unable to step outside of it to see its true nature. This does not mean the pursuit is futile. On the contrary, it reframes the quest. The goal shifts from simply cataloging the contents of the cosmos to deciphering a profound and subtle code written into the expansion of space and the growth of structure. Every new telescope, every massive simulation, is an attempt to read a few more lines of that code. This reality instills not despair, but a profound sense of awe and humility. It is a reminder that the universe owes us no easy answers, and that its greatest mysteries are not puzzles to be quickly solved, but landscapes to be explored for generations. The fact that we are here, a collection of atoms born from stars, able to perceive this vast darkness and ask these immense questions, is itself a wondrous thing. Our familiar world of light and matter may be a minority in the cosmic census, but it is the part that wonders, that seeks, that strives to understand the deep and beautiful darkness from which it came. This philosophical layer adds a necessary gravity to the scientific journey, transforming it from a technical challenge into a fundamental human exploration, a testament to our relentless curiosity in the face of the magnificent and overwhelming unknown. The next great leap in this cosmic investigation is already taking shape, not on a mountaintop, but on the drawing boards and clean room floors of the world's space agencies. To move from inference to understanding, we need data of a quality and scale that dwarfs everything that has come before. This is the goal of a new generation of observatories, instruments designed from the ground up to be forensic detectives for dark energy. Among the most ambitious is NAS, a Nancy Grace Roman Space Telescope, named for the pioneering astronomer who paved the way for space-based observatories. Scheduled for launch later this decade, Roman is not just another telescope, it is a cosmic census taker with a revolutionary wide-field view. Its primary mission is to stare deeply into vast swaths of the sky, capturing the light of billions of galaxies across more than half the age of the universe. It will perform two critical and complementary measurements with exquisite precision. First, it will discover thousands of distant Type 1, a supernova, those same stellar explosions that first revealed acceleration, but with a consistency and volume that will map the expansion history with unprecedented detail. Second, and perhaps even more powerfully, it will perform a technique called weak gravitational lensing on a colossal scale. This involves measuring the subtle, systematic distortions in the shapes of millions of distant galaxies. These distortions are not caused by flaws in the telescope, but by the invisible scaffolding of dark matter that warps the fabric of space-time along our line of sight. As light from faraway galaxies travels toward us, it passes through this cosmic web, its path gently bent. By statistically analyzing these tiny shears in galaxy shapes, astronomers can create a three-dimensional mass map of the dark matter distribution across the universe. This map is a direct record of how structure has grown over cosmic time, and because dark energy suppresses that growth, its repulsive fingerprint will be encoded in the map's details. Roman will essentially take an X-ray of the cosmos, revealing the skeleton of dark matter and showing exactly how the push of dark energy has stunted its development. The telescope's immense field of view allows it to collect this data over an area hundreds of times larger than the Hubble Deep Field in a single snapshot, making such a monumental statistical analysis possible for the first time. The goal of Roman and its contemporaries, like the European Space Agency's Euclid mission already in operation, is to achieve percent-level precision on a single, crucial number, the equation of state of dark energy. Think of this number as dark energy's identity card. If it is exactly -1, it confirms the simplest model, Einstein's cosmological constant, a static energy woven into space. If the measurement deviates from -1, even by a tiny amount, it will be a revolution. It would mean dark energy is dynamic, something like quintessence that changes over time, pointing toward entirely new physics. These next-generation probes offer our best hope yet within the coming decade to answer the foundational question: is the engine of acceleration a fixed feature of the void, or is it a changing field with a story of its own? The answer will not just solve a puzzle, it will choose our universe's ultimate destiny, steering us toward the quiet freeze or a more dramatic end. But to truly appreciate the strangeness of our accelerating present, we must look back to the most violent and mysterious fraction of a second after the beginning. The universe we see today, vast and smooth on the largest scales, was born from an event of unimaginable violence called cosmic inflation. In the first fleeting moments, a trillionth of a second after the Big Bang, a bizarre form of energy is thought to have taken hold. This energy, often described as a scalar field, possessed a repulsive gravity so fantastically powerful that it caused space itself to expand faster than the speed of light. In less than a blink, the entire observable universe was blown up from a subatomic speck to a size larger than a grapefruit, smoothing out any wrinkles and planting the tiny quantum seeds that would later grow into galaxies. Then, just as suddenly as it began, this inflationary field decayed, its energy transforming into the hot, dense soup of particles that began the conventional Big Bang expansion. For decades, inflation stood alone as the universe's only known episode of runaway acceleration, a brief, explosive prologue to the slower, matter-dominated story that followed. Then we discovered dark energy. Now we live in a second epoch of acceleration, a gentle but relentless push that began billions of years ago and continues today. The parallel is impossible to ignore. Both are periods where the expansion of space accelerates, driven not by matter or radiation, but by a dominant, smooth form of energy that exerts negative pressure. Both act as cosmic bookends, one at the very beginning, setting the stage for all structure, and one in the late-time universe, determining its ultimate fate. This mirroring raises a profound and tantalizing question. Are these two bookends fundamentally connected? Could dark energy be a faint, distant echo of that primordial inflationary field, a remnant that never completely switched off? Or perhaps inflation and dark energy are two separate manifestations of a similar kind of physics, a type of energy field that can, under different conditions, cause spacetime to stretch at an accelerating rate. Exploring this possibility challenges our models across the entirety of cosmic history. It suggests that the same underlying principles might govern the universe's birth and its death, that the engine that ignited creation and the force that will dissolve it into emptiness could be relatives in the family of physical law. Yet the differences are just as stark. Inflation was unimaginably brief and incredibly powerful, a cosmic shout. Dark energy is weak, subtle, and persistent, a cosmic whisper that has already lasted billions of years. The inflationary field had to decay violently to heat the universe, while dark energy simply endures, unchanging as far as we can tell. Are these differences in strength and duration merely a matter of setting different dials on the same cosmic machine, or do they point to two completely distinct and unrelated phenomena? This question ties the fate of the future directly to the mysteries of the origin, forcing us to consider whether the entire story of the cosmos, from its first instant to its last, is a single, continuous narrative written by a recurring theme, the strange, repulsive gravity of empty space. A powerful scientific consensus is not the end of inquiry, but an invitation to scrutiny. While the evidence for cosmic acceleration is robust, a handful of physicists and cosmologists urge caution, asking whether we might be misreading the cosmic signals. Their criticisms do not dismiss the observations, but challenge the interpretation, proposing that the appearance of acceleration could be an illusion created by our own limited perspective or by flaws in our theoretical framework. One provocative line of thought questions a fundamental assumption of modern cosmology, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. But what if it is not? What if we live inside a vast cosmic void, a region of below-average density stretching for billions of light years? In such a place, the gravitational pull from the denser matter outside our local bubble would be uneven. This imbalance could, in theory, create a local motion that makes it appear as if distant galaxies are receding faster than they truly are, mimicking an accelerated expansion without any dark energy at all. It would be like standing in a valley and misjudging the speed of hikers on the distant ridges because your own ground is subtly sloping. Proponents of this idea argue that we cannot simply assume perfect smoothness. We must prove it, and that our location might be special in a way that skews our measurements. Another family of critiques focuses on the tools we use to measure the vast cosmos. Our entire chain of reasoning depends on standard candles, like Type 1, a supernova, and the precise interpretation of their redshift. But what if our understanding of how these supernovae evolve over cosmic time is imperfect? Could ancient supernovae be intrinsically fainter for reasons we do not yet grasp, making them seem farther away, and thus implying a faster expansion? Or perhaps the interstellar dust that dims their light is distributed in more complex ways than our models account for, subtly corrupting the data. These are not claims of error, but calls for humility, reminding us that every measurement is filtered through layers of interpretation and assumption. The most radical alternatives, however, go straight to the laws of physics themselves. We have discussed modified gravity theories, ideas that tweak Einstein's equations to produce cosmic acceleration from ordinary matter. While none have yet succeeded in matching all observations, they represent a fundamental philosophical choice. Is it more likely that the universe is filled with a mysterious, dominant energy we cannot detect, or that our theory of gravity, however brilliant, is subtly incomplete on the largest imaginable scales? This tension is the engine of scientific progress. These skeptical viewpoints are not fringe ideas. They are essential counterweights that force the mainstream to strengthen its case. Every potential systematic error must be hunted down. Every alternative model must be tested against the growing mountain of data from the cosmic microwave background, galaxy surveys, and gravitational lensing. So far, the standard model with dark energy has passed every rigorous test, fitting the independent lines of evidence with remarkable precision. The consensus is strong because it is earned through conflict and verification, not declared by decree. Yet this healthy skepticism serves a vital purpose. It keeps the question open. It ensures that as new telescopes like Roman and Rubin come online, they are not just confirming what we expect to see, but actively searching for the cracks in the prevailing theory. The story of dark energy is not a finished book, but a living investigation where today's best answer remains perpetually on trial, awaiting the next witness from the depths of space. The profound questions raised by dark energy belong not just to researchers in isolated labs, but to anyone who has ever looked up at the night sky and wondered. Translating these immense, abstract concepts into something tangible and inspiring is a vital part of the scientific journey itself. Think of the classic classroom analogy of an expanding universe as a balloon with galaxies drawn on its surface. As you inflate the balloon, every dot moves away from every other dot. Now, to illustrate dark energy, imagine someone begins to blow into that balloon not with a steady breath, but with a pump that increases its power with every second. The dots do not just separate, they flee from one another at an ever faster rate. This simple visualization, while imperfect, provides an intuitive anchor for a deeply counterintuitive idea. It transforms a complex equation about negative pressure and vacuum energy into a physical action we can picture. Planetariums around the world have embraced this challenge, crafting immersive shows that fly audiences through the cosmic web, letting them witness the accelerating expansion of space across billions of simulated years. These are not passive lectures, they are experiences designed to evoke awe, making the scale of the mystery felt on a human level. Beyond the dome, interactive websites and apps allow anyone to explore the latest data from telescopes, toggling different models of dark energy to see how they would reshape a virtual cosmos. Perhaps most empowering are the citizen science projects that invite the public to become active participants in cosmology. Thousands of volunteers help classify the shapes of distant galaxies in telescope images, data that is crucial for weak gravitational lensing studies, directly contributing to the map of dark matter that dark energy distorts. This collaborative effort demystifies the process of discovery, showing that science is a collective human endeavor built on curiosity and careful observation. By making these frontiers accessible, we do more than share knowledge, we ignite a spark. A student captivated by the balloon analogy today might be the researcher who solves the cosmological constant problem tomorrow. More broadly, it fosters a public appreciation for the grand, ongoing quest to understand our universe, reinforcing that the biggest questions about existence are not reserved for experts in white coats. They are open invitations extended to everyone who possesses a sense of wonder. The story of the accelerating cosmos is ultimately our shared story, a narrative about our place in a reality far stranger than we imagined, and that is a story worth telling to everyone. The search to understand dark energy has done more than map the cosmos. It has reshaped the world we live in right here on Earth. This deep, curiosity-driven quest for fundamental answers rarely stays confined to the abstract. The immense technical challenges of measuring something so elusive have forced us to invent entirely new tools that are now transforming medicine, technology, and our global capacity for innovation. Consider the very eyes of our modern telescopes, the charge-coupled devices, or CCDs, that capture the faintest photons from the edge of time. To study dark energy, we needed sensors of unprecedented sensitivity and stability, capable of imaging billions of galaxies with perfect clarity. The relentless push for better detectors has directly advanced the field of digital imaging. The same core technology now powers sophisticated medical imaging devices, allowing doctors to see inside the human body with stunning detail for earlier and more accurate diagnosis, from detecting tumors to mapping brain activity. This is not a coincidence, it is a direct technological transfer from the mountaintop observatory to the hospital wing. Then there is the challenge of the data itself. A single night at an observatory like Vera C. Rubin can generate terabytes of information, a flood of raw numbers about galaxy shapes, colors, and positions. Making sense of this deluge required us to invent new languages of analysis. scientists developed advanced machine learning algorithms and statistical techniques to find subtle patterns in this ocean of data, to separate the true signal of cosmic acceleration from a universe of noise. These very algorithms, born from cosmological necessity, are the progenitors of the sophisticated artificial intelligence and big data analytics that now drive innovation everywhere, from improving weather forecasting and managing financial markets to optimizing global supply chains and personalizing the digital world. We learned to teach machines to see the universe, and in doing so, taught them to see patterns that improve life on our planet. Perhaps the most profound spin-off exists in the realm of pure computation. To test theories of dark energy, we build universes inside machines. These cosmological simulations are among the most computationally intensive tasks ever conceived, requiring global networks of the world's most powerful supercomputers to run for months. The drive to create these digital twins has pushed the entire field of high-performance computing to new heights, advancing processor design, data storage solutions, and the very architecture of how we link machines together to solve grand challenges. The techniques forged in these virtual cosmos are now applied to model equally complex systems, like the global climate, the folding of proteins for drug discovery, and the dynamics of fusion energy reactors. We built supercomputers to simulate dark energy, and in the process, built a foundation for solving some of humanity's most pressing problems. Beyond the hardware and software, this quest has forged a new model of global cooperation. Projects like the Dark Energy Survey and the Euclid space mission are not the work of a single nation or institution. They are vast, international collaborations involving hundreds of scientists from dozens of countries, all sharing data, resources, and expertise toward a common, profound goal. This framework of open, borderless science, built on shared curiosity, is a powerful legacy. It demonstrates that humanity can organize on a planetary scale to tackle the deepest questions, a model of diplomacy and shared purpose that yields not just cosmic maps, but enduring partnerships and a pipeline of cross-cultural innovation. The story of dark energy reminds us that the greatest return on investment is not always the direct answer we seek. By funding the pure, ambitious desire to understand our universe, we inadvertently seed the ground for technological revolutions and cooperative frameworks that enrich society in countless, unpredictable ways. We reach for the stars and our hands come back holding tools that heal, connect, and empower the world below. The stars have always been our first and most profound teachers. For thousands of years across countless cultures, humanity looked up and saw a celestial sphere, a perfect, unchanging dome that rotated around our central, stationary Earth. This geocentric model was not born from ignorance, but from the direct, undeniable evidence of our senses. The sun rose and set. The planets traced complex but predictable loops against the fixed backdrop of stars. It was a beautiful, orderly, and deeply comforting cosmology that placed us at the very heart of creation. This model, refined by brilliant minds like Ptolemy, held sway for over a millennium. It was not just a scientific theory, it was a philosophical and religious bedrock, a story that explained our place in the grand scheme. Then, in the 16th century, a quiet revolution began. Nicolaus Copernicus, armed with little more than mathematical elegance and a profound intuition, proposed a shocking alternative. What if the sun was at the center and Earth was just another planet in motion? This heliocentric model was initially met with resistance, not only because it challenged authority, but because it demanded a radical psychological shift. We were no longer the pivot point of the universe. This was the first great cosmological demotion, a humbling realization that the patterns in the sky were not about us. It expanded our vision from a small, Earth-centered stage to a solar system, setting the stage for an even greater expansion to come. The journey from that Earth-centered dome to our modern view was not a straight line. It was a series of profound corrections, each one pushing our home further from the spotlight and revealing a universe vaster and more mysterious than we had dared to suppose. Centuries after Copernicus, Edwin Hubble used the Great Telescope on Mount Wilson to deliver the next monumental shift. Those faint, fuzzy nebulae were not clouds within our own Milky Way. They were entire galaxies, island universes in a sea of darkness. And they were all rushing away from us. The universe was not static. It was dynamically expanding, carrying the galaxies along like raisins in a rising loaf of bread. This discovery of cosmic expansion was another staggering demotion. Not only was our planet not central, our entire galaxy was just one among billions, adrift in an ever-growing cosmos. It gave us a universe with a history, a beginning in the hot, dense state of the Big Bang. For decades, this became the new paradigm, a cosmos born in fire and slowly cooling, its expansion gradually slowing under the relentless pull of gravity. We settled into this new story, believing we finally understood the broad strokes of cosmic evolution. Then, at the close of the 20th century, the distant light of dying stars told us we were wrong again. The expansion was not slowing, it was speeding up. This discovery of cosmic acceleration marks our latest and perhaps most profound cosmological demotion. We have learned that not only are we not central, and not only is our galaxy ordinary, but the very stuff we are made of, the atoms and light that constitute our familiar reality, is a mere 5% of the cosmos. The dominant forces are dark and unknown. This historical arc from the geocentric dome to the accelerating void reveals a powerful pattern. Each time we build a complete and satisfying model of the universe, the cosmos itself provides new evidence that shatters it, forcing a grander, more humbling, and more wondrous view. The mystery of dark energy is not an anomaly. It is the latest chapter in this ongoing story of discovery. It tells us, in no uncertain terms, that our current cosmological model is almost certainly provisional. Just as Ptolemy could not have conceived of a sun-centered system, and just as astronomers before Hubble could not fathom an expanding universe, we today may be blind to the next great truth. The accelerating cosmos suggests that future discoveries, perhaps from the next generation of space telescopes or from a brilliant theoretical insight, could once again radically alter our conception of reality. This is not a cause for despair, but for exhilaration. It means the adventure of cosmic discovery is alive and vibrant. The universe continues to be a patient teacher, offering clues in the redshift of galaxies and the whisper of vacuum energy, waiting for us to ask the next right question. Our history shows that each time we accept a demotion in our cosmic status, we are rewarded with a far more magnificent and intriguing universe to explore. The story of cosmic acceleration is not just one of data and equations, but of people. It is a tale of two teams working on opposite sides of the world, racing toward the same impossible conclusion. Saul Perlmutter led the Supernova Cosmology project based at Lawrence Berkeley National Laboratory. His group approached the problem with a meticulous, almost industrial mindset, developing automated systems to scan the skies for the telltale flashes of distant supernova. Across the Pacific, the High-Z Supernova Search Team, spearheaded by Schmidt, and with crucial analysis led by a young Adam Riess, took a different tack, relying on the sharp eyes and intuition of a close-knit group of astronomers. For years, both teams endured the grueling cycle of modern cosmology, battling for precious time on the world's largest telescopes, often working through long, cold nights, only to have their observations ruined by a passing cloud or a technical glitch. The goal was straightforward: measure the deceleration of the universe. They expected to find a gentle slowing, a cosmic sigh. What they found instead was a growing sense of unease. As the data from their most distant supernova trickled in, it stubbornly refused to fit the expected curve. The numbers whispered a heresy. The universe was not slowing down. Both teams independently arrived at this terrifying possibility. In those private moments, doubt was a constant companion. Adam Riess would later recount checking and rechecking his code, searching for a bug, an error in the dust models of distant galaxies, anything that could explain away the faintness of those ancient stellar explosions. Schmidt described the period as a slow, creeping realization, a feeling that they were staring at something that would turn their field upside down. They scrutinized every assumption, subjected their work to brutal internal review, knowing that if they were going to claim something this monumental, they had to be bulletproof. The pressure was immense, compounded by the knowledge that another team was likely seeing the same strange signal. The moment of shared realization, when the two groups finally compared notes at a conference in 1998, was not one of triumph but of profound shared shock. They had not set out to rewrite the textbooks. They had simply followed the data, and it had led them to a cliff's edge. Announcing their findings to the world felt less like a victory lap and more like stepping into a void, presenting a conclusion that challenged a century of accepted cosmology. Their personal journeys, filled with late nights, stubborn problems, and the courage to trust uncomfortable evidence, remind us that science is a deeply human enterprise. It is forged in collaboration and friendly competition, driven by perseverance, and illuminated by those rare, exhilarating moments when the universe decides to reveal a secret it has kept for billions of years. These researchers did not just calculate an accelerating expansion. They lived the visceral experience of discovery, a reminder that the maps of the cosmos are drawn by curious individuals who dare to ask nature a question, even when the answer threatens to dismantle everything they thought they knew. The human response to a cosmic mystery is rarely confined to the pages of a scientific journal. When a discovery as profound as the accelerating universe emerges, it sends ripples far beyond the observatory, seeping into the very fabric of our culture, art, and storytelling. This unseen force pushing the galaxies apart has become a powerful modern metaphor, a canvas upon which artists, musicians, and writers project our deepest questions about change, the unknown, and our place within an indifferent vastness. In galleries around the world, visual artists have begun to translate cosmological data into immersive experiences. Some create sprawling installations where points of light, representing galaxies, slowly drift apart at an ever-increasing pace, controlled by algorithms based on the real equations of dark energy. Visitors do not just learn about acceleration, they feel it, surrounded by a silent, visual representation of the universe's relentless expansion. The data becomes a medium, and the mystery becomes a sensory encounter, transforming abstract numbers into an emotional resonance. This is not mere illustration, it is a dialogue where art provides a visceral language for a concept that mathematics alone can struggle to convey. The haunting, empty beauty of these works often evokes a sublime mixture of awe and loneliness, directly mirroring the philosophical weight of the science itself. In music, composers have experimented with themes of cosmic acceleration, using stretched time signatures, gradually increasing tempos, and vast, droning soundscapes to create auditory illusions of an expanding void. The concept of dark energy, an invisible presence, finds its echo in ambient music that emphasizes negative space and subtle, pervasive tones that seem to emanate from the silence itself. These pieces invite listeners to contemplate scale and emptiness, using sound to explore the emotional texture of a universe dominated by the dark. The acceleration becomes a rhythm, a slow, inevitable crescendo that shapes the entire composition, much as it shapes the fate of the cosmos. Perhaps the most accessible realm of this cultural absorption is literature and film. Science fiction authors have eagerly incorporated dark energy and the accelerating universe into their narratives, not as textbook concepts, but as plot devices and backdrops for profound human drama. They imagine civilizations struggling to communicate across ever-widening gulfs of space as the expansion accelerates, a metaphor for isolation and the fading of connections. Stories explore ships using dark energy as a power source, or entire species facing extinction as their local group of galaxies is ripped apart by the Big Rip scenario. These tales use the science as a springboard to ask timeless questions about legacy, memory, and what endures in a universe whose fundamental rules seem to guarantee dissolution. In film, the visual spectacle of an accelerating cosmos offers breathtaking imagery, but more importantly, it provides a narrative framework for existential stakes that feel truly universal. When a film's conflict hinges on the fate of all existence, dark energy provides a scientifically plausible, yet deeply mysterious antagonist or catalyst. This cultural reflection does something essential. It democratizes the wonder. Not everyone will follow the intricacies of supernova surveys or the cosmological constant problem, but anyone can be moved by a painting, a song, or a story that channels those ideas. This intersection of science and art creates a vital feedback loop. The science provides the raw, awe-inspiring material, the profound questions about reality. The art, in turn, processes that material through the lens of human emotion, giving it narrative shape, aesthetic form, and emotional depth. It allows us to engage with the mystery of dark energy, not just intellectually, but viscerally. We do not simply understand the acceleration, we can fear it, marvel at it, and mourn the solitude it implies. This creative processing highlights a profound truth. Our most fundamental questions about the cosmos are never purely scientific. They are inherently human. The urge to map the stars and the urge to sing about them spring from the same source, a deep need to find meaning, connection, and beauty in the vast, dark, and accelerating expanse we call home. By giving this cosmic mystery a face in our art and a voice in our stories, we are not simplifying it. We are meeting it on our own terms, weaving it into the ongoing human saga, and in doing so, acknowledging that to wonder about the universe is one of the most defining acts of being alive. This fine-tuning for existence feels almost too perfect to be an accident. Our universe's dark energy is not just present, it is calibrated within a breathtakingly narrow window. If its repulsive strength were even slightly greater, the story of cosmic structure would have ended before it began. In those first critical moments after the Big Bang, a stronger dark energy would have overwhelmed gravity's gentle pull, smoothing out the tiny density fluctuations that were the seeds of all future galaxies. The cosmos would have expanded into a vast, featureless, and eternal emptiness with no stars, no planets, and no possibility of observers. Conversely, if dark energy were slightly weaker, or even negative, gravity's grip would have been absolute. The universe would have expanded only briefly before succumbing to a catastrophic big crunch, collapsing back on itself long before the first complex molecules could form. We exist in a cosmic sweet spot, a razor's edge between sterile emptiness and premature collapse. This Goldilocks condition, where dark energy is just right for the emergence of complexity, forces a profound question upon us. Is our accelerating universe a universal rule, or is it a cosmic peculiarity? When we look out at our cosmos, we are studying a single data point. We have only one universe to observe, which makes it incredibly difficult to distinguish between what is necessary and what is merely possible. Is a universe with a cosmological constant like ours the only kind that can logically exist, dictated by fundamental laws we have yet to uncover? Or is it simply one version among many, a single roll of the dice in a much grander casino? This is where speculative ideas like the multiverse enter the conversation, not as proven science, but as a framework to grapple with the staggering fine-tuning we see. In a hypothetical multiverse, a vast or infinite ensemble of separate cosmic domains, the physical constants could take on every possible value. Most of those domains would be stillborn, expanding too fast for any structure or collapsing too quickly for any history. But in a vanishingly small fraction, by pure chance, the numbers would line up in the life-permitting range. We, of course, find ourselves in one of those rare, hospitable pockets, not because the universe was made for us, but because we are a product of its rare conditions. From this perspective, the mystery of dark energy shifts. The question is no longer why does dark energy have this specific, perfect value, but why do we observe this value? The answer becomes self-selecting. We are here to ask the question because this is one of the few cosmic environments where questioning beings could evolve. This idea can feel unsettling, as it suggests our entire cosmic home might be a statistical fluke in a much larger, mostly barren reality. Yet it also reframes the fine-tuning from a miraculous puzzle into a potential clue about a deeper, more varied cosmic landscape. It challenges us to consider whether the laws of physics we hold as immutable might instead be local bylaws, effective rules that emerge within our particular cosmic bubble. The accelerating expansion we measure, then, might not be a fundamental feature of all reality, but a contingent feature of our particular universe, one thread in a tapestry of unimaginable diversity. Whether one finds the multiverse idea compelling or a step too far, it underscores the profound strangeness of our situation. The dominant force in our cosmos appears exquisitely tuned to allow for our existence, a fact that demands some form of explanation. It pushes cosmology beyond pure physics into the realm of deep philosophical inquiry, asking us to consider not just how our universe works, but why it is the way it is, and whether, in the grand scheme of all possibilities, a universe that wonders about itself is a common thing or the rarest treasure of all. Language itself becomes a cage when we try to describe the cage's own architect. We are beings of matter. Our senses and our words evolved to navigate a world of solid objects, palpable forces, and direct cause and effect. We speak of energy as something that flows, that can be transferred, that makes things happen. But dark energy resists this vocabulary at every turn. It is not a flow, it is a condition. It is not transferred, it is simply present. It does not make things happen in the way a wind pushes a sail. It alters the very geometry of the arena in which everything plays out. When we call it a form of energy, we are using the closest word we have, but it is a profound approximation, like calling the ocean a very large puddle. Our intuition, honed by millennia of survival on Earth, is worse than useless here. It actively misleads us. We instinctively think of empty space as nothing, a passive stage. Dark energy tells us the stage itself is the most active participant, stretching its own boards at an accelerating pace. This creates a profound cognitive dissonance. We can write the equations that describe its effect. We can calculate its influence to many decimal places, but we struggle to form a mental picture of what it is. Is it a field, a fluid, a property? The words feel clumsy, like trying to describe a color to someone who has been blind since birth. This linguistic barrier is not a minor inconvenience, it is a fundamental part of the scientific struggle. Researchers are not just hunting for data, they are fighting to build a new conceptual framework, a new set of metaphors that can bridge the gap between the mathematics of the vacuum and the human mind. They speak of negative pressure and an equation of state, terms borrowed from thermodynamics, but these are analogies, attempts to map the unknown onto the slightly more familiar. The mathematics, cold and precise, becomes the primary language, while our everyday words lag far behind, pointing feebly at a reality they were never designed to capture. This forces a humbling realization. Some aspects of the cosmos might be inherently indescribable in the language of human experience. We may be able to know dark energy only through its shadow, to understand its rules without ever truly visualizing its essence. Our comprehension might always be indirect, a translation from the pure dialect of mathematics into the imperfect, earthy tongue of stories and pictures. This does not mean the quest is meaningless, but it reframes success. The goal becomes less about crafting a perfect mental image and more about learning to trust the map, even when the territory it describes is a form of reality our senses were never built to navigate. A telescope mirror polished for cosmic mapping might seem a world away from a hospital scanner or a climate model, yet the immense financial and human investment required to chase a mystery like dark energy forces a difficult but vital question. In a world facing urgent challenges, from health crises to environmental strain, can we justify spending billions of dollars and decades of effort to study the acceleration of distant galaxies? This is not an abstract debate. It is a real ethical consideration at the heart of big science. Projects like the Roman Space Telescope or the Vera C. Rubin Observatory represent a staggering commitment of public funds, international coordination, and the focused careers of thousands of brilliant minds. The argument against such investment is straightforward and morally compelling. That capital and expertise could be directed towards solving immediate human suffering, building resilient infrastructure, or developing clean energy solutions. When a child lacks access to clean water or a community faces the impacts of a changing climate, the precise value of the cosmological constant can feel like the most distant of luxuries. Critics rightly ask if this pursuit of pure knowledge is a privilege we can afford, a diversion of resources from the tangible needs of our planet and its people. This perspective demands our respect and serious consideration, for it roots itself in a profound empathy for human hardship. To dismiss it is to ignore the very real weight of earthly responsibility. Yet the defense of this curiosity-driven research is equally profound, and it begins by challenging the notion that such science is a diversion. History shows us repeatedly that the quest to understand the fundamental nature of reality rarely stays in the realm of the abstract. The technological demands of peering deeper into the cosmos have consistently generated revolutionary spin-offs. The need to process the faint light of distant supernova drove the development of the digital camera sensors now used in every smartphone and medical imaging device. The algorithms created to find subtle patterns in galaxy surveys form the backbone of modern machine learning, tools now applied to everything from diagnosing illness to optimizing renewable energy grids. The supercomputers built to simulate universes are the same machines modeling complex climate systems and designing new materials. The investment in cosmic questions does not vanish into the void. It seeds the ground for unpredictable, transformative innovation here on Earth. The path from a cosmological equation to a life-saving technology is never a straight line, but it is a well-trodden one. Furthermore, these monumental projects are not national endeavors but global ones. The search for dark energy has forged unprecedented international alliances, bringing together scientists, engineers, and institutions from nations with complex political relationships. They collaborate under shared protocols, sharing data and credit, building a framework of trust and common purpose that exists outside of traditional diplomacy. This cooperative model, born from a shared human curiosity about our universe, becomes a quiet but powerful bridge, demonstrating that our greatest challenges, whether cosmic or terrestrial, are best met through collective effort. On a deeper level, this pursuit speaks to something fundamental about our species. We are not merely creatures of survival, we are creatures of story and meaning. To look up and ask why the heavens are arranged as they are, to seek our place in the grand narrative of time and space, is an impulse that defines human culture. It is the same impulse that drove the builders of ancient observatories and the painters of celestial ceilings. This quest for understanding is not a luxury, it is part of what makes a civilization. It inspires new generations to study science and engineering, it fuels our imagination, and it provides a humbling context for our planetary existence. The knowledge that we live in an accelerating universe dominated by a mysterious dark energy changes our perspective. It teaches us about humility, about the fragility of our assumptions, and about the breathtaking scale of reality. This cultural and intellectual enrichment is a real, if intangible, return on investment. The ethical balance, therefore, is not a simple choice between space and society. It is the recognition that investing in fundamental questions is also an investment in our long-term capacity to solve problems, to cooperate globally, and to nourish the curious spirit that drives all human progress. The funds dedicated to mapping dark energy also map the frontiers of our technology and our collective potential. In seeking to understand the fate of the cosmos, we may ultimately learn more about how to shape a better future here at home. The most honest map of the cosmos we possess is one drawn in pencil, not ink. Our current model, with its dark energy and accelerating expansion, is the best explanation we have, fitting the evidence with remarkable precision. Yet to treat it as the final, definitive word would be to forget everything we have just learned from history. The journey from a static celestial sphere to an expanding universe, and then from a decelerating expansion to an accelerating one, is not a story of steady progress toward a single truth. It is a story of repeated revolution, where comfortable, well-established models were shattered by stubborn new data. Each time, the cosmos revealed itself to be stranger, grander, and more mysterious than we had allowed ourselves to suppose. This pattern is not a bug in the scientific process, it is the very engine of discovery. The provisional nature of our understanding is not a weakness, it is science's greatest strength. A scientific theory is not a monument to be defended, but a tool to be used, tested, and discarded the moment a better one comes along. Our model with dark energy is that tool today. It organizes the observations, makes predictions, and guides the next generation of experiments, but it lives under a constant, healthy suspicion, perpetually on trial against the evidence of the universe itself. This means the puzzle of dark energy is not a frustrating dead end. It is an open door. It is the clearest sign we have that our exploration of the cosmos is vibrantly alive, that we are standing on the edge of a frontier, not at the end of a road. The next great shift in our cosmic story could come from anywhere. It might arrive in a flood of unexpected data from the Vera C, Rubin Observatory, revealing a subtle crack in the dark energy model that no simulation predicted. It could spring from a brilliant theoretical insight, a new way of linking the quantum world to the curvature of space-time that makes the cosmological constant problem simply dissolve. Or it might depend on an instrument not yet conceived, a telescope orbiting at a gravitational sweet spot or a detector buried deep underground, designed to catch a whisper from a dimension we do not yet know exists. The acceleration of the cosmos is not an answer, it is an invitation, a cosmic question mark written in the flight of galaxies. To engage with this mystery is to participate in that grand human tradition of looking at the stars and daring to redraw the map. The universe has surprised us before, it is almost certainly preparing to surprise us again. The connection between these two mysteries, the quantum vacuum and the cosmic void, is a bridge across the largest possible scale in nature. It spans from the realm where time and space themselves lose meaning to the vast, cold emptiness between galaxies. This bridge is not yet built, but its blueprint is being drawn by the most ambitious ideas in theoretical physics. At the quantum scale, empty space is not empty. It is a seething, chaotic froth, often called quantum foam, where virtual particles and antiparticles constantly wink in and out of existence. This frenzy gives the vacuum an enormous, thrumming energy. Yet when we look out at the cosmos, we see the effect of a vacuum energy that is almost exactly zero, a quiet hum so faint it only reveals itself by pushing galaxies apart. The difference between these two energies is not just large, it is the largest discrepancy ever measured in science. This tells us, in no uncertain terms, that our two most successful theories, quantum mechanics and general relativity, are speaking different languages about the same void. They are giving us two completely different answers for the energy of nothing. Dark energy is the glaring symptom of this disconnect. It is the observable proof that something is deeply wrong or deeply incomplete in our understanding. To resolve this, physicists are searching for a single, unified theory, often called quantum gravity, that can seamlessly describe both the behavior of the tiny vibrating strings or loops that might make up space-time and the curvature of the cosmos on the grandest scales. In this quest, dark energy is not a side note, it is the central clue. Any candidate theory of everything must do more than just marry the equations. It must naturally explain why the furious quantum buzz of the vacuum cancels itself out to such an exquisite degree, leaving behind only the gentle, smooth residue we call dark energy. It must answer why the energy of the void is not enormous, but almost precisely the tiny value we observe. This makes the accelerating expansion of the universe a cosmic laboratory, a natural experiment testing the deepest foundations of reality. The precise rate of acceleration, the way it has changed over billions of years, these are numbers that any successful theory of quantum gravity must be able to predict or accommodate. We are no longer just astronomers measuring galaxies. We are detectives examining a clue left at the scene of creation, a clue that points toward a hidden unity behind all the forces and particles we know. The journey to connect the quantum foam to the cosmic void is perhaps the greatest adventure in human thought, and dark energy is the signpost telling us we are on the right path, even if the destination remains shrouded in beautiful, profound mystery. Every star you see in the night sky is a testament to a delicate cosmic timing. The atoms that form your hands, the air in your lungs, and the ground beneath your feet were forged in stellar furnaces that could only exist because the universe expanded at just the right pace. This is the deeply personal fingerprint of dark energy. Though its push is too gentle to feel across a room or a planet, its influence across billions of years is written into your very biology. For most of cosmic history, gravity held the upper hand. Its relentless pull allowed matter to clump together, forming the first stars and galaxies from the primordial soup. This was the era of construction when the cosmic cities were built. If dark energy had been stronger, if its repulsive push had dominated too soon, that gentle clumping would have been overwhelmed. The universe would have expanded into a thin, featureless haze before any galaxy, any star, any planet could ever form. We would not exist in such a place. Conversely, if dark energy were absent or weaker, gravity's grip would have been absolute. The universe might have collapsed back on itself long ago, cutting the story short. The fact that we are here, on a stable planet orbiting a long-lived star, means dark energy switched from a background whisper to the dominant voice in the cosmic conversation at precisely the right moment in cosmic history. It allowed gravity enough time, nearly 10 billion years, to build the rich tapestry of galaxies and stars, including our own Milky Way and our Sun. Then, as the universe grew larger and more diffuse, dark energy's constant energy density finally overcame gravity's fading pull, beginning the accelerating era we now inhabit. Your existence is perched on that pivot point. The carbon in your cells was fused in a star that formed during that window of gravitational dominance, a window defined by the specific, gentle strength of dark energy. So when you look up, you are not just seeing points of light. You are seeing the aftermath of a 13 billion-year competition. You are seeing the structures that gravity built, now being carried apart on the silent, accelerating current of dark energy. That grand, invisible force is not just out there. It is in the history of every element that makes you, a fundamental part of the story that led, against astonishing odds, to a conscious moment gazing back at the stars. The journey from that first shocking day to point to our current cosmic map has been one of profound humility. We began with the simple, logical expectation of a slowing universe, only to watch it dissolve in the faint light of ancient exploding stars. In its place, we found acceleration, a runaway expansion pointing to a dominant, invisible presence we named dark energy. This is not a minor puzzle. It is the central feature of our reality, making up most of the cosmos and dictating its ultimate fate. The evidence for it is now a chorus, from the detailed patterns in the primordial afterglow to the stunted growth of the cosmic web, all singing the same unsettling tune. Yet for all its overwhelming influence, dark energy remains a profound enigma, a placeholder for our ignorance. It suggests a form of energy we barely understand precisely because it exists at the violent intersection of our two greatest theories, the quantum world of the impossibly small and the relativistic cosmos of the impossibly large. Each theory gives a wildly different answer for the energy of empty space, and dark energy is the observable symptom of that catastrophic disagreement. We are left staring at a universe where the rules we know best describe only a tiny sliver of what exists. The path forward from here demands a threefold pursuit. First, we need ever more precise observations, the kind that next-generation telescopes will deliver, to measure the properties of dark energy with forensic detail and see if it truly is constant or something that changes. Second, we require bold theoretical innovation, ideas brave enough to bridge the chasm between quantum mechanics and gravity, to explain why the vacuum hums with this specific, gentle energy. And finally, we may need the courage to embrace radically new conceptions of space, time, and the void itself, ideas that might feel strange or unsettling because they describe a reality far outside our everyday experience. The accelerating universe is not a dead end for cosmology. It is the most exciting beginning. It is a doorway, not a wall. This mystery, written in the flight of galaxies, is an open invitation to develop a more complete and profound understanding of physical reality than we have ever possessed before. The cosmos is patiently waiting, offering clues in the dark for us to take the next step. The most profound discoveries often leave us not with answers but with better questions. Our journey through the accelerating cosmos has revealed a universe far stranger than the one we learned about in school, a reality where the dominant force is an invisible, repulsive energy we can neither see nor touch. Dark energy is not a remote fact for textbooks. It is a direct and humbling challenge to our deepest understanding of space, time, and existence itself. It whispers that the empty void is alive with a mysterious tension, that the familiar laws we rely on are incomplete, and that the fate of all galaxies is written in a language we have only just begun to decipher. This is not a story with an ending, but one with an open invitation. The universe has shown us it is still capable of breathtaking surprises, reminding us that our maps of reality are always provisional, always ready to be redrawn by the next observation, the next brilliant insight, the next generation looking deeper into the dark. So the next time you find yourself under a clear night sky, let that feeling of wonder return. Those points of light are not just stars, they are markers on a vast, accelerating expanse, a cosmic mystery playing out on a scale beyond human imagination. Our quest to understand it is one of the great adventures of our species, a collective effort to illuminate the darkness with the light of curiosity. The conversation about our universe, its origins, and its ultimate fate is just beginning. If you want to follow that conversation as it unfolds, consider subscribing for more journeys to the edge of our understanding. And we would love to hear your thoughts. What does the mystery of dark energy make you wonder about our place in the cosmos? Share your reflections in the comments below.